Let's do another example for linear momentum. In this problem, 148, chapter 3, we have two boxes on this incline, box A and B, and we have the mass of both of them. So the mass A is moving at the beginning with velocity of 4 meters per second downward, and we have friction between the box and ground. The other one is stationary at the beginning. It's not moving. So this box moves down and finally hits the second box, box B. After hitting this one, they're gonna attach to each other and then move downward. And the question is how much they're gonna move together down the incline. I would suggest to think about this problem for 10 minutes before seeing the rest of the video. So we need to start by calculating the acceleration of this box. So this box is moving at the beginning, the velocity of it is 4 meters per second. But at the end, when it hits the second box, I don't know what is the velocity of it, right? But I can calculate it. To do that, first I start by drawing the free body diagram of box A. So for this box, we have mass of A times G, gravitational force. We are gonna have normal force from ground. And also we are gonna have friction force. Because it is sliding down, the friction force is gonna be mu K times N. And let's call this direction X and this one Y. So in this free body diagram, sum of the forces in the Y direction is equal to 0 because there is no movement in the Y direction. And from there, the normal force is going to be equal to mg times cosine of theta, which is 15 degrees here. So N is going to be mass of A times G times cosine of theta. And then sum of the forces in the x direction is going to be mass times acceleration in the x direction, which is going to be the total acceleration because it is moving just in the x direction. So sum of the forces in the x direction is equal to mass of the box times acceleration. And in the x direction, the forces are mg times sine of theta. This angle is going to be theta. And also mu k times n in the negative direction. So we are going to have ma g sine of theta minus mu k times n, and we know n is ma g cosine of theta. So this is n. All is going to be equal to ma times acceleration. And from here, we are going to find the acceleration of the box. ma is going to cancel out from both sides of this equation, which means the acceleration is going to be totally independent from the mass. So acceleration of the box is going to be g times sine of theta minus g times mu k times cosine of theta. And in this specific problem, theta is equal to 15 degrees, mu k is given, it is 0.4. So from here, acceleration is going to be equal to negative negative 0.1276 times g. And the acceleration is constant, right? So acceleration is constant. We know the initial velocity and we want to find the velocity after traveling 3 meters down the incline. So we know the displacement, we know initial velocity, and we know acceleration. We want to find the final velocity. I mean the velocity that hits the box B. So the best equation to find the velocity at this point is going to be the time-independent equation for constant acceleration, right? So the velocity at this point, velocity of box A, at this point, if I call it V, it's going to be velocity squared minus initial velocity squared, which is 4 meter per second, is equal to 2 times acceleration times displacement, and the displacement is 3. So s minus s0, which is 3 meter. Velocity at the beginning is 4, so by putting all the numbers, velocity is going to be equal to 2.91 meter per second. So this is going to be the velocity of box A before impact. Now the problem says box A is going to hit this one and they're going to attach together, and both of them are going to move down. Let's say after sticking together, they're going to move with the velocity of v bar. Okay, so they're gonna attach together and they're gonna move with the velocity of a. Now you need to consider two moments: immediately before impact and immediately after impact. Before impact, the velocity of box B is 0, velocity of box A is 2.91. And immediately after impact, velocity of both of them is going to be v bar because they are moving together. And in between, if you look at the free body diagram of these two, in the x direction, we are going to have mg, the forces in the x direction is going to be mass of both of them times g times sine of theta. And also, we are going to have friction force in the x direction, in the negative x direction. So G2 minus G1 is equal to sum of the forces dt based on the equation that we learned, right? But we need to consider that the duration of the impact is very, very short. So 1 means before impact, and 2 means after impact. And the duration, the impact is very, very small. So if you look at this equation that we are writing it for between before impact and after impact in the x direction, we are going to have something here which is not equal to 0, right? Because we are going to have gravitational force in the x direction and also the friction force in the negative x direction. So the sum of the forces is not equal to 0. It's going to be something. It's going to be a constant number. And also, again, we are considering both of them as our system, right? So the impact force between these two is not going to be in this sum of the forces. That's going to be an internal force. So we are going to have something here which is not equal to 0, but t is very close to 0 because the duration of the impact is equal to 0, is almost 0. It's very, very short. So the integral of whatever we have here from 0 to t, which is a very, very small number and close to 0, is going to be almost 0. So because of that, G2 is almost equal to G1. So if we neglect that small this small number which comes from this integral, we can say G2 is equal to G1. So what is G2? The linear momentum of the system after impact is going to be mass of both of these boxes times the velocity of them, which is v bar. And before impact, we know the velocity of A is going to be 2.91 and velocity of box B is going to be equal to 0. So we are going to have ma times the velocity of it. So linear momentum of box 1 or box A plus the linear momentum of box B, which is 0, right? So from here, like the previous problem, we are going to be able to find the velocity of the system after impact. It's going to be mass A, which is 10, divided by the total mass of our system, which includes both of these masses. It's going to be 16 times the velocity of mass A before impact, which is 2.91. And if you calculate this, it's going to be 1.821 meter per second. So this is going to be the velocity of both masses together, which stick together after impact. So after impact, again, both of them are going to move down with the constant acceleration, which we calculated before. We calculated this for box A, but if you want to calculate the acceleration of both boxes after the impact when they are stick together, you're going to get exactly the same thing, right? Because as I showed you here, the acceleration down on the incline is going to be independent from the mass of the system. So if you write this equation for mass A or mass B or combination of them, you are going to get the same acceleration. Now, after impact, the initial velocity is going to be this. Acceleration is going to be the same thing that we found here. And we want to find how much they're going to travel down the incline. So again, we can use the time independent equation here. So when it goes down, both of them, at the end, the velocity is going to be equal to 0. Velocity final, let's say. So velocity at the end is squared minus initial velocity, which is this v bar, is going to be equal to 2 times acceleration times the displacement, which we're going to call it d. So if we put the numbers, velocity at the end is equal to 0, and velocity at the beginning, which means after the impact, is going to be 1.821 squared, is equal to 2 times acceleration. Acceleration is negative 0.1276 times g times the displacement. The total displacement will stop. So if you calculate, put these numbers in your calculator, d is going to be equal to 1.326 meters.